All right. So whatever we've talked so far, right? We've been talking about motion of straight line. We said, well, remember we established the straight line, and so this is the we define the unit vector in the direction of the motion, and we said, well, this is the direction. This unit vector gives us information about the direction, positive or negative, and S pretty much is the position. Because S by itself doesn't give us enough information. It just tells us where it is located. It gives us the magnitude of distance, I would say, or better say distance. Distance is just a number. And then vector, unit vector could give us the positive, negative, or directionality, or where we are with respect to origin, either on the right side or on the left side, depending on which side you get as positive or which side you get as negative. All right, now we're just going to expand this, and we're going to start looking at what happens if this motion we are studying or looking at, we want to know, again, the same story, position, velocity, acceleration. We want to look at these three in a case in which the motion is not on a straight line, right? Some curvature, some curved line, whatever it is. So I'll put it under motion, motion on a curvilinear, hopefully I spelled correctly, curvilinear path. Now we're going to start. So the motion on a curvilinear path, or curve on a curve is not straight, pretty much. We can study that using different, I would say, coordinate systems. We're going to look at the most straightforward one is just to use XYZ coordinate, right? Cartesian coordinate system. And then we'll look at tangent normal coordinate system and how we can use that to study such motion. And finally, polar coordinate system, right? R theta. I will see there is a very, very tight relationship between tangent normal and polar coordinate system. We'll get there. But we're going to start with Cartesian coordinate system. We have a particle, we have a point moving in space, right, in some direction. It's not a straight line motion anymore. And we want to know how can we study its motion using Cartesian coordinate system, assuming that we are studying that in a Cartesian coordinate system. So I put one here, but the second and third is going to be a while from now. We have to cover this and then the second one, third. Or let me just put everything at the beginning right here. We can study the motion of a particle on a curvilinear path in different coordinate systems. Including Cartesian coordinates, different coordinates, you can think about that this way. Tangent normal, coordinate, and polar coordinates. So just put it here, polar coordinates. And let's start with the straightforward one, which is basically Cartesian coordinate. I'll give you the general form in three-dimensional space, but we're not going to actually do it in three-dimensional space. We're just going to stick to two-dimensional space, pretty much X and Y. But it depends on how you set the coordinate system. It might be in YZ plane, it might be in XZ plane, but we're always in two-dimensional space. Axes might change, but we're always in just one plane. So let me just draw it here. What I'm trying to say is that if this is x, and the coordinates should be right, and then so that would be x, y, and z. Right? Depending on how you look at it, they're always in one plane, at least within the scope of this course. Xy, yz, or xz. Now, if we have, again, general form, if we have a point, let's say P, a particle, with the coordinates of x, y, z somewhere in the space, and let's draw the position vector r that we talked about before, right? Basically represent where this particle is in the space. I would just represent that in Cartesian coordinate system. Nothing new, hopefully, for you guys. If you think about these as unit vectors, this is I, this is J, and this is K. I usually use tiny hat to represent unit vectors. I try to do it. Sometimes I just get lazy. I ignore it. But or as a position vector, right? The vector that represents where this point or particle P is in the space. General form would be xi plus yj plus zk. It's a very general form of that. And from our definitions, we know the velocity is basically just the derivative of position with respect to time. So you take derivative from first one is xi, it becomes dx dti plus di dtx, right? It's a derivative of a multiplication. Unit vector doesn't really change, right? Its magnitude is 1, doesn't change. Its direction also doesn't change. So its derivative with respect to time is 0. So that part we can ignore. What happens is that you'll only get dx dti plus dy dtj plus dz dtk. And typically we show these with vx, vy, vz, just for shorter representation. So you can, if I put it this way, this would be vxi plus vyj plus vzk. I'm going to put it here. So Vx is nothing but dx dt, Vy is dy dt, and Vz is dz dt. I'll actually put it in, because that's, consider that as a relationship that you'll use. This is just V. Components of V. This is also a vector. Same story for acceleration, right? It's just pretty much the derivative of velocity. So acceleration following the definition. dv dt. Now, same story, dv dt. Vxi is the x component, so becomes dvx dt times I plus di dt times vx di dt, as the unit vector doesn't change. Its magnitude is 1, its direction is always constant. So the derivative with respect to time for that vector is 0. What you're going to end up having is just dvx dt in I direction. dvx dt I plus d, I can do better a little bit, dvy dtj plus dvz dtk, which again you can just represent that ax, these are just notations, ayj plus azk. Same story as velocity. A x, let me do a better job this time. Actually, I'm going to cheat. maybe not. AX is dVx dt. Right? AY is dVy dt, and AZ is dVz dt. Pretty much it. I really try to. All right. All right, nothing unusual there. Taking derivative, and let's also keep this as something you need to pay attention to. Now, what is the most common? So this tells me that if I know where this particle is at any given time with respect to my coordinate system, XYZ coordinate system, and given the fact, or assuming that I know that how XYZ coordinate for that particle change with time, I can find velocity and acceleration by just taking derivative with respect to time from each component. That's the definition. Now, from this definition, there is one famous type of motion that you've probably seen, but that basically the equations that you use are coming from this Cartesian coordinates, using Cartesian coordinates to study curvilinear motion on a curvilinear path. And that would be the projectile problem that you've seen when we throw something. You throw a ball in physics, I guess you've seen it. You throw a stone, given some initial angle and some initial velocity. You want to know how far it goes, depending on what problem is trying to put in front of you. But the general form would be a projectile problem. Right? So it's an example of a problem in a Cartesian coordinate system. We can take a look at the general form and then look at some examples of how can we actually use those equations. But that's pretty much the only type, I would say the main type of the problems you deal with in two-dimensional or in Cartesian coordinate system when the motion is on a curvilinear path. Then I'll look at the very specific one that is not projectile problem. But that type of problem is pretty much the most important problem that falls into this category, I would say. So, for example, we can, we can derive, the equations for a projectile problem. What I'm trying to say is that, let's say we have coordinate system XY. Some projectile, let's say, we're assuming that it is exactly at the origin, right? And we know its initial velocity. So actually, let me use a different color. So it's exactly here. And we throw it, or we give it, or it's given some initial velocity. Let's use a better color there. It's given some initial velocity, V naught. This is V naught, and that creates an angle theta with, and I called it theta naught, the initial angle. So we have something, some stones, some balls, some whatever you want to think about, some moving, something that projectile problem. We just throw it, and then we know its initial velocity. We are assuming in this case to derive the equation, we just put the coordinate exactly where it is. And we know the angle, initial angle that initial velocity makes with the x-axis, the horizontal line. So how do we deal with this? There you go. We have to find, if you go back to what we have position, or we have velocity, and we have acceleration, nothing else. So we have to start from somewhere. Now, one thing we know about this problem we can come up with the acceleration components. When you throw it at t equals to 0, it's given some initial velocity, and it's just, that's it. Right? So the assumption for these problems go as this: ax is 0, acceleration in x direction. Acceleration in y direction is minus g, gravity is pulling it down. And acceleration in z direction is also 0, it's in xy plane. So this is the assumption that you have for this problem at t equals to 0. And you can also add this projectile is at the origin with initial velocity v naught in xy plane and angle theta naught, sake of completeness. So we have everything there. This is the problem you're facing. So ax is 0. We'll see what we can get from there. Ax is 0. Those are the given information. So we'll just use them to find the relationships between position, velocity, and acceleration. When ax is 0, well, we know dvx, ax is dvx dt, which means that is 0. That tells me that vx is constant, because its derivative with respect to time is 0. Vx is constant. What does that mean? It means whatever the component of velocity is in x direction at the beginning of the motion, it's going to be the same for the whole motion. So this particle is moving. Doesn't matter what happens for the rest of the motion, assuming these assumptions that ax is 0 and ay is minus g. The velocity, the x component of velocity, right now we're in a Cartesian coordinate system, so velocity has an x. In this case, we're in two-dimensional space, so velocity has an x component and velocity has a y component. X component of velocity is constant, meaning that whatever it is going to stay the same. Now, what that constant value is, if you look at xy, that constant value is basically the component of v naught on x-axis at the beginning. We know v naught, we know theta dot, so that component is v naught cosine theta naught. So vx for this motion is v naught cosine theta naught. That's pretty much it. That's what we got from ax is equal to 0. Now from ay is equal to 0, minus g, I don't know where to get that, minus g, we'll see what we get from there. Actually, let's continue this line of thought. We have vx now, so we can find. Now, once we know vx is dx dt. So vx is equal to dx dt is equal to v naught cosine theta naught. What does this tell me? It tells me if you calculate the integral or take integral from both sides, I'm just going to write it, dx from 0 to some x is equal to integral v naught cosine theta naught dt from 0 to some t. So that will be x is equal to v naught cosine theta naught t. That's it. So the position at any given moment is initial or velocity in x direction, v naught cosine theta naught, multiplied by time. So we can now know that what is the x component of velocity at any given moment, which is a constant number, so it's the same during the motion, and where that object is in terms of x component of the position. Remember, R is xi, yj in this case. We're in two-dimensional space. Now, what we need to know is in two-dimensional. We also need to know what is Vy and what is y, right? To have a good picture of velocity and position. Because right now we only have x component of velocity and x component of position. We need to know y component of velocity and y component of position to have a good picture of where this particle is or object is at any given time. So we go with the second piece of information that we're given. Ay is equal to minus g. Now Ay is dvy dt, and this is minus g. So Vy, if I just, let's actually do the whole process. If I move things around, this is an integral. dvy is equal to integral g dt, negative there. All right? No complaint, hopefully, so far. We're just following math, wherever it takes us. Now, Vy changes from whatever is the initial Vy. Right? So I'll put it Vy naught to Vy, wherever it is at some given moment the velocity is. Time changes from 0 to t. I'll just go with 0. You might have some t naught there. Just for simplicity, I'm assuming that we are at t equals to 0. So this becomes, now here's the question. What is Vy naught? I need to know this limit for my integral. I can actually find that. What is the initial component of V naught?
Would it be VO sine theta?
Exactly. So it would be V naught sine theta. Coming from the coordinate system, we have V naught and we know theta naught. That's the beginning of the motion. All right. Hopefully that makes sense. So we move things around. Vy becomes, if I move things to the other side, minus gt plus V naught sine theta naught. This is going to be my Vy. So now I have a picture, good picture of velocity at any given time. X component of velocity, Y component of velocity, right? This is X component. That's not what I want to do. This is the X component of velocity. This is Y component of velocity. We can get Y as well, right? So we know Vy is dy dt. Move things around. I'll skip one step. Dy goes from 0 to y is equal to integral from 0 to t. Well, I know what Vy is, minus gt plus V naught sine theta naught dt. You do this math, you will get y is equal to minus 1 over 2 gt squared plus, let me be a little more general here because we are going to need this. Let's say we have some y naught. And I'm going to do the same thing here. Don't kill me for that, but that helps to save some time later on. Is I'm going to change the assumption here. Projectile is, let's say we don't know if it's exactly in the origin with initial velocity of this. So I can change this to x naught. So we just get the more general equations. We don't know if it's exactly in the origin. So that would be x naught. I'm going to extend this a little bit. Plus x naught And here also I'm going to get V naught sine theta naught t plus y naught. Just to get something more general. You could always assume that y naught is 0 and we are in the origin, and that just eliminates that. So also we have the components for position. So at any given time, using this general idea about motion on a curvilinear path, at any given time, we know what is the velocity because we know it's two components, Vx and Vy, right? V is, the final idea is that V is Vxi plus Vyj, and R is Xi plus Yj. So at any given moment, I know the position and I know the velocity. Remember, all we're doing is we want to know the relationship between position, velocity, acceleration. Any given moment, now I know what velocity is, and I know what position this particle is located at, because I knew the accelerations. This is just, we throw it and we are given, that assumption should hold though. The ax and az are 0, and the only component of acceleration applied to this particle is just g, gravity, pulling it down. Right? So for this example, as one type of example of curvilinear motion, we now have the full picture of relationship between position, velocity, and acceleration. Question on this one. Remember, everything just started from this simple representation and definitions we had. Now we know what the relationship is between those three things that we care about for our motion.